My name's Muratori. I'm a game developer, which, as I could sort of tell from the last talk and the quality of service packets thing, is probably not the common person who's at this conference. So, just to sort of give you some background on the talk, when they asked me to speak here, I was like, okay, that sounds cool, but what do you want me to talk about? Because it doesn't seem like the kind of thing that has really any game development content. And they were like, well, we just want to know, like, what do you guys do when, have you used research? How do you use it? Give us some examples of times when you use research and it's inspired you to do something cool, I think was the way that it was phrased. And so I was like, okay, I can do that. So what I've done is I've picked 3 papers from way, way back in history. So, not way, way back in history, but way back in my history. They're very early papers for game development that are really pretty important. They're used for a lot of things, and which I had sort of a personal relationship with. Like, I read the papers and really loved them and then did some work in the game industry that was related to them, and I'm going to kind of go through those. Now, my assumption is that since it's not a game developer-centric conference, that people don't already know these things. That's why I picked sort of foundational ones. I apologize if you're a game developer, you're going to be like, I already know this stuff already. So what can I say? All right, so the other thing to say is, this is actually how my slides will look. This was kind of the, like, you're coming in and I don't want you to be scared away. But that's actually what my slides look like, because I tend to, like, scribble things really fast as I'm going, and that's just like, it's okay, I'm going to explain it all. You don't have to read the slides really hardly at all. They're usually just there for diagrams that I need to sort of, like, refer to. Like, look at the thing on the top, look at the thing on the bottom. Okay. So from here on out, I'm going to be going very, very fast. I'm going to be going on 2x speed, like on the little YouTube drop-down, because again, I'm assuming you're not going to go home and implement these papers. So I'm going to skip over some things, and I'm going to talk pretty fast. I'm thinking you're just going to want to see sort of what sort of stuff we're doing and how it sort of works, but you don't necessarily need to go home and write it. If you do, that's even better. Come up and talk to me afterwards. I can talk to you all about it as much as you want. Okay. So let's go back to 1996, which I'm old, so that's actually, I was, what, 18, 19, something at the time. So it's actually not that long ago in my mental history, but it probably seems long for some of you who weren't even born then. Okay, so 1996, this was my first job out of high school, actually, and I was working on a game development project. And the reason that I kind of wanted to start here is because, ironically, and for this conference, it actually happened to be a job based entirely on a paper. Now, this is not one of the papers I'm actually going to be talking about that I have loved. I'm not saying I don't love it, it's just not one of the 3. It's kind of like, if you've ever been to like a restaurant, one of the fancy restaurants, where they say like there's going to be 3 courses, and you order that, but then this thing comes out at the beginning, and they're like, sir, this is not one of the courses, this is an amuse-bouche. This is the amuse-bouche. Like, this is the thing that you're gonna, it's like, creamed celery with a crouton or something, I don't know what. So just, that's not one of the papers. I don't want to get the wrong idea. But this is actually a pretty interesting paper. It's called Evolving Virtual Creatures by a guy named Carl Sims. He worked at a company called Thinking Machines, which was a supercomputer company back when supercomputer meant like the thing that you guys are carrying as phones right now. That is like what he worked on, right? But at the time, they were massively powerful. Okay. So what they did in this, in this paper, and I guess I shouldn't say they, because I guess it was just he. I don't remember ever seeing any co-authors mentioned or anything. He actually made a system that sort of like simulates nature, like for reals. He made a sort of a concept of DNA that could encode both the morphology of a virtual creature and how it behaved. So like a sort of a, it wasn't really a neural network kind of thing, but it was sort of like a little controller logic sort of graph thing that could make the creature actually actuate its joints. And they made an actual physical simulation inside the, inside the supercomputer, and they could run these virtual creatures through tests, right? They could kind of give them things to do and see what they did. Now, of course, since the whole point of this thing is to simulate nature, what they were doing is they would randomly generate some of this DNA, and they just let whatever creature popped out with crazy morphology, whatever it had, and whatever stupid, really bad brain, just stumble around. But they would then grade all of the random creatures on how well they did. So for example, let's say that the creature needed to get from one end of the thing to another. There's an obstacle in the middle of it, right? They would see how far the creature was able to get, and they would rank them. So they kind of had an idea, like, of all the creatures, these are how they are, right? They would then take those, and genetic algorithms were mentioned earlier in the patch talk, right? They would take those and they put them in a genetic algorithm. They take the trees for their morphologies and their brains, and they would just do sort of like a sexual reproduction thing. Let's pick some from this one, let's pick some from this one, merge them together, and then have some kind of a parameter we can tune for random mutations, right? And shockingly, as I'm saying this I think was in 1993, 94. You should go look at the paper if you're interested in this stuff, because it's a fun read, and there's videos on YouTube of the crazy creatures doing their thing. So I'd highly recommend looking at it if this piques your interest at all. But point being, this is a long time ago. You would expect this to fail completely, but actually it was pretty good, right? Like the things that come out of it are actually really neat, and they kind of can do a bunch of things, like following a light source or getting over an obstacle or things like that. So it's actually pretty cool. But what wasn't necessarily pretty cool is the fact that somebody thought, well, I know who they were, but I won't mention them. Somebody thought that it would be a good idea to make a game based on this concept. Now, in the abstract, that's a very good idea. But when you think about the context in which this paper was really implemented, it was on a CM5, which is a thinking machine supercomputer, like I said. It is a supercomputer at that time, 32 CPUs, which is actually a high number of CPUs even today. Most gaming machines don't technically have 32 CPUs, even though some of them, well, it depends on what kind of gamer you are. Maybe they do have 32 CPUs, but most of them don't. And it took 3 hours to run one of these things. So if you think about what you were trying to do in that era in terms of turning that into a game, it's just stupid. It's just a ridiculous idea, because you only had one CPU and it ran at 120 megahertz, right? And you only had like 10 seconds or something probably. I mean, how long is a user going to wait in a like, hey, all right, I'm generating some creatures. You're not going to tell them to come back in 3 hours. Like, no one's going to want to play that game, right? So this was doomed to failure. But fortunately for me, that part wasn't my job. My job in this particular context was to create the environments in which the creatures would do whatever their thing is, what they were going to do. And the mandate was sort of that these environments would kind of be like organic-y. Like they would be like, let's say we were making like viruses or something inside the human body. So where these things would play out would be inside a human body, or something that felt kind of like if you were watching an episode of, I don't know, again, this is the old cultural references, House, let's say, and they zoom into the bloodstream, and it's like what's going on with the chemicals and that sort of stuff. It should look kind of like that, all right? So that's what they told me to do, and remember, I'm very little. I mean, I wasn't actually, this is an age and experience thing, not a height thing. I didn't get this short when I was 18. That would be weird. But point being, basically, I didn't know very much about research in any particular way. Right? I had not been to college. I don't really know what that means. But at this point in time, they said, well, constructive solid geometry is a thing that a lot of game engines are using now. It's kind of a new thing. If you remember this era at all, for those in the audience that do, there are games like Quake and Unreal and these sorts of things, and they were using constructive solid geometry to build their levels. Now, there's a lot of reasons for that we don't need to go into because they're not relevant. But point being, I was sort of told, go look at that because that's generally how levels are built, figure out how that works, and off you go. Now, this was like a totally new thing for me to do because I didn't know anything about how to find papers or how to find constructive. I have no idea. And the internet is kind of this like blossoming flower at this point, right? It's kind of a thing that like, well, we have a 14.4K baud modem or whatever that was at the time. It makes the noise like the noise when you connect. That's how you got onto the internet if you weren't at a university or something like that that had a really like serious connection. And so that's the kind of thing that we were doing. And at that point, Sightseer, I think, had sort of started to come up. So the idea of going onto the internet and getting papers and sort of that sort of thing was kind of exciting and new, and I was really like into it. I was like, oh, this is great. So I started sort of crawling through these papers and like, okay, constructive solid geometry, let's see. And what happened was kind of just a fortuitous, reading through papers and you're like, oh, that looks interesting. I found a paper that talked about something called AlShapes. And AlShapes, I don't even know how to search for it anymore. I tried a little bit, sort of half-heartedly a little before to see if I could dig it up, but I couldn't. So I don't even remember the context in which they were being talked about. But basically they were talking about this concept that when I have two shapes and I want to kind of merge them together, couldn't I do something that made them kind of blobbily go together instead of rigidly going together? And if you look at this drawing here on the side, you can see that there's two things. The one on the top, the exclamation point next to it, is kind of the blobby coming together. And you can imagine in your mind the difference between that and if you took, say, two circles and put them over each other, you get kind of a cusp there, right, where they intersect at that sort of intersection, at that cuspy point. And that's not very organic, because organic things are very cellular, that sort of thing. Unless you're talking about like a tusk or something like this, usually they tend to kind of blob together. And certainly in the sort of things we were looking at, like inside the human body, you would expect these smoothnesses. So I'm like, oh man, this could be perfect for what we want to do. And for those of you who don't really know kind of what I mean with the blobby come together, again, if anyone can remember back to like Terminator 2, anyone Terminator 2, or is that way too far back? Okay, got a couple people. Okay, so Terminator 2, there's like this weird cyborg metallic alloy guy, right? He can form into things, and like occasionally stuff happens, like he freezes and he shatters. And then things turn back into these little blobs, and the blobs start like forming together, right? And they kind of, as they get closer together, they kind of like sort of suck into each other, you know what I mean? Like mercury, if you've ever seen that happen. So basically that is the thing that this paper led me to. I started looking at the AlShapes thing, and it turned out that AlShapes are like not this really, I guess, not very interesting or whatever, because most of the literature on doing those actual kinds of things with surfaces was in the implicit surface literature. That's what it's called, right? Implicit surfaces, I will sort of give you an idea of what they are now, because if you're not familiar with games or graphics, you probably never heard of them or don't care about them. But what they are is, instead of modeling with things concretely, which is what we're kind of more used to doing even in most software packages that people who don't work on serious 3D modeling would experience. If you're in something like Adobe Illustrator or something like this, then you're used to, I'm making solid shapes, and I'm saying this is kind of exactly the shape that I want, and then I'm done, right? But what implicit surfaces are sort of like modeling more with like potential energy fields, right? It's sort of like saying, I might take some shapes and I'm going to use them to model, but instead of thinking as the actual shapes as the input, it's actually like this energy field that they give off that's the actual thing I'm modeling with. And what happens is when you move two of these shapes together, you get constructive interference. So what happens is as their energy fields overlap, something happens in there. And don't worry, I'm going to tell you what the something is. You don't have to imagine. And point being, if I want to define a surface, like an actual thing that I modeled from this kind of a thing, I can simply say, let's find where the energy equals some number, and I can pick out kind of a band as it goes, right? And you can see, where that constructive interference was. Everything else kind of follows the shapes exactly, but where the constructive interference is, you can see that you get that curvature. And the reason is because those fields are adding together. They're creating like an additive constructive interference that creates sort of curved bending stuff that happens there. And that's exactly where we wanted, that was sort of in my mind. It's like that's where we want to go to get that organic feel, right? Now, there's something interesting that I should say about this that's relevant to the rest of this, which is that when you have a definition like this, you end up with some interesting things that just sort of magically happen. One of the things that's actually very difficult to do, well, very difficult, that's probably the wrong term. One of the things that might be a little bit difficult to do, if you have a traditional definition of a shape or a surface or something like that, is to say what is inside the surface and what is outside the surface. And one of the reasons is because the surface might not be complete. It might not really be enclosed. There's all kinds of reasons it might not be. But even if you know that the surface is completely closed, and you want to ask a question like, am I inside it or am I outside it, then you have these problems of like, okay, I have to start doing like an intersection testing, and there's robustness problems with this potentially, like, did I do the intersection testing properly, and all these other sorts of things, right? But with an implicit surface definition that works with these energy fields, it's actually extremely easy to know whether you're inside or out, because the whole definition of the surface is based on some kind of a field like this. So at any point, you know if I'm outside, if I'm inside, or if I'm on the surface, because the definition directly gives you that information. So it kind of flips the problem around from explicit modeling, where I'm just saying what the shell of something is. It turns out that it's exactly inverse. With an implicit function or an implicit surface, I know immediately whether I'm inside or outside at any point in the world. But what is actually relatively difficult to do is define the entire surface in some concrete way that I could render or whatever, because all I know is kind of, can I tell if I'm there or not? Whereas with explicit surfaces, it's the opposite. I know exactly what the shell is, but I have to do real work to figure out whether I'm inside it or outside of it. Okay. So anyway, for those of you who like mathy sorts of things, these are not particularly difficult maths at all. Like the math for implicit surfaces is basically trivial, unless you're doing some very specific things. But point being, all they are is their field functions. They take some point in space, my f of x, y, z up there on the slide, and they produce some real value, like a scalar out the other end. And that scalar is kind of the energy that I was referring to. So at any point in space, and it doesn't matter what kind of space this is. It could be 2D, it could be 3D, it could be 1D, it could be 9D. It does not matter. It's some function where you input a point in the space that you're talking about, and out comes that value, right? Now, oftentimes, I should kind of point out that, the value that comes out of it, I sort of said, back in the slide, I was like, well, if we want to define the surface, we can sort of pick what energy level we use to figure out what the surface is that we actually want. And well, actually, if you care about the math of it at all, that's not really how it works. When you pick that energy level, you usually end up kind of making a new function where you subtract that energy level away, because whenever you're talking about math things like this, it's always more convenient to talk about 0 as being the solution, right? So you kind of want to talk about 0 as being where the surface is. So we end up with this convention where when I input something into this function, when I get 0 out, I am on the surface, exactly on on the surface. When I get something greater than 0, I am inside the surface. And when I get something less than 0, I am outside it. Sorry, did I say those right? Hopefully I said those right. If not, the slide is right. Don't listen to me. All right. And once again, for those of you who like math, it's so simple, the math behind basically the implicit surface modeling functions. One of the most common ones is metaballs, which is just a point field, right? It's just saying, here is a point, and I kind of get a little spherical energy field around that point. And the way that those are implemented is just 1 over the distance. That's it. Like, if I want to know a point in space, how much is it influenced, how much energy does this metaball contribute, it's just 1 over the distance to the ball. That's it, right? Nobody ever uses that, and the reason is because it doesn't have finite support, which is something you don't care about at all unless you're going to implement these. So you usually use something else that's just kind of fitted to that function, but it's basically that. You're just going to make some little optimizations. So again, really simple math for the implicit function. But the part that wasn't so simple until this paper, right, is that we essentially have 3 steps to this thing. If I actually want to take an implicit surface function, which I just said is incredibly easy to do the math for, but I want to get out the actual surface, right, then I have a problem. In step 1, I can trivially just take as many implicit surfaces as I want, and they're additive fields, so I can add them all together. I can make some crazy modeling program that has as many different kinds of things that I want in it. And they don't have to be metaballs, it can be anything. Any function you can imagine that goes f, x, y, z can be in there, right? There is no limitation on it, because all I need at the end of the day is a scalar, right? That's sort of what we're saying. And then step 3, if we leave out magic step 2, is I have the actual surface, right? I have something that I could feed into, say, a standard OpenGL rendering pipeline, or something that I could output to an OBJ file, or something. OBJ meaning wavefront OBJ, not a compilation OBJ. I realize this is a language conference. I won't make that step again. Something you can output into a PLY file, let's say that. Okay. So that's where the first paper I love comes in. It's called Marching Cubes, and it's got a really long subtitle. It's kind of like one of those nonfiction books where they have like one really simple word and then 50 words that tells you exactly what the content of the book is. It's that kind of a title, but this is the paper. It's by Lawrence and Klein. And what it was, I think it was mainly developed kind of for medical imaging, because they sort of have this sort of problem there in other ways. But it's a way of filling in that missing step 2 where all the question marks were, okay? Now, here's how the paper works, okay? I need to figure out some way, something to get some traction on this problem. I have an entire world filled of values that I can evaluate, but I have no idea where the surface actually is. And furthermore, if you think about what happens, assuming that it is just a surface, a 2D surface, right, embedded in a 3D space, takes up almost none of the space. That's kind of how 2D, like a volume squared is always much lower than cubed, no matter what the value is that you pick, unless you're less than 1. So anyway, you kind of have this problem of the chances of you randomly finding the surface are like none. Like, you're never going to do it. You're never going to guess a point that's 0. It's not going to happen unless it's an incredibly weird field. So usually you're going to guess some other points. So we kind of need to figure out, just to get some traction on the problem, how do I even know where a 0 is? Just give me something to work with here, right? And so what I can do is I can pick 2 random points anywhere in the field that I want to, and I can evaluate the implicit surface at those points, right? That's trivial for me to do. I just said it's easy math, and really we're just running through some equations. Just put in the x, y, z, out comes a scalar, and we're done, right? So there's only 3 cases that could happen when I do that. The first case is that they both return positive values, which means they're both inside the surface, right? The other case is they could be both outside the surface. And in both of those cases, right, they both return less than 0, they're both outside the surface. In both of those cases, I have learned absolutely nothing about what happens in between these 2 points. And the reason I have learned nothing about that is because I don't know if the field kind of came in and just touched some of those middle points there. So I could have been both in and both out, but missed what happened in the middle, right? But the third case is the important one. If one of them is less than 0 and the other one isn't, then I finally do know something about what happens in between, and more importantly, I know exactly the thing that I wanted to know. I know that the surface is in between, right? Because in order to go from a positive value to a negative value along the line between them, at some point I had to have crossed 0, at some point. Even if the function is discontinuous, the discontinuity hadn't happened between us, right? So it's going to happen. And that's all I need to know. Once I know that, any of you who are familiar with numeric computation, this should be very, very familiar to you. It's basically root finding. All I need to know is, well, okay, take the line between them, bisect it, sample it there. What's the result? That will tell me which way to go, right? If the result is the same result as A, then I want to go towards B more. If the result is the same as B, I want to go towards A more, right? I want to push away from the one that I got the same of. So I'm just going to keep hopping till I get to where the surface is, right? And get to where the surface is kind of an ambiguous phrase at this point, because really, we're sort of, as we're bisecting, we're never probably going to get exactly 0. So really what I mean is just go down to the precision you actually care about. And that doesn't actually hand wave unless you're one of these people who does big nums or fortune algorithm or all those sorts of other things where you actually compute exact results for things. But assuming that you're computing on an actual computer with actual IEEE 32-bit floating point, you only have 24 bits really to work with anyway, so 24 steps of a bisection will get you to the most accurate answer you could possibly have anyway, right? So there isn't even any inaccuracy to this if you want to run it all the way. Okay, so last step to the algorithm. Now we know that if I have 2 points, and I see if there's one's positive and one's negative in terms of valuing the function, I can find where the surface is, right? So now the question is, how do I go from that to an actual representation of the whole surface that I could use? And this is where the marching cubes thing comes in. It's pretty cool. It's very simple, very elegant. You can implement it trivially. It's really nice in that way. I just can imagine in the 2D case I've got on the left side, in the 3D case I've got on the right side, you either take a rectangle or a cube, and you evaluate the points, all 4 of them or 8 of them, depending which one we're talking about. And what you will get is a series of positives and negatives, right? They'll all be negative, they'll all be positive, some negative, who knows? What you then can do is take any edge that is coming off a positive and going to a negative and do that root finding step that I just talked about. You now know where the surface crosses the rectangle or the cube, right? And all that's left to do is connect them. And now you've got either an outline of your surface or a triangulation of your surface, as long as you just do this to basically the entire area that you care about. And you can see that this is a pretty easy thing to kind of compartmentalize. If you think about the way positives and negatives can actually work on these things, if you have a rectangle, there's 4 points, there can only be 2 to the 4th combinations, right? There can only be 16 combinations of positives and negatives in this thing. So you only have to implement 16 cases. And by the way, those 16 cases really aren't 16 cases because they're highly symmetric. If only 1 point is positive and the other 3 are negative, well, it's the same case just rotated, right, to a couple different ways. So you really only have to implement a few cases, and then you just have to figure out which one you're looking at and maybe rotate the problem a little bit, but then you're still using that one case. Same is true for the cube. Worst case, you typed in 256 things, but really it's not even close to that because most of them are just symmetric versions of the same exact problem. And then, like I said, you just apply this to your entire plane area that you want to figure out what the surface looks like there, or the volume. And I didn't draw the volume because, oh my God, like my drawing skills are not up to that. But you can imagine what happens if you just march the cubes through there one at a time, figure out what the triangles are, you will just get a mesh that occupies that volume and is exactly where the surface is, all right? So hopefully, does that make sense? Am I going too fast? Because I know I'm going fast, but are we good? We're totally good. Okay, awesome, that's what we need to know. Let's go, okay, brief moment of silence, little tiny moment of silence. There was gonna be a little brain teaser in here, it got cut for time. Okay, 1999, we're gonna go 3 years forward here. All right, I don't know where that is on my height to age thing that I did before, but we're gonna go 3 years forward to 1999. And this, I was working on a character animation system. This was not a crazy project. This was actually a good project. So this was reasonable. This was not something sort of conjured up by people who have ludicrous ideas of what's possible. Okay, so working on a character animation system. And one of the things that's true about animation in general, if you've ever worked with it, is that rotations are a really, really big deal in terms of what you're gonna have to deal with. And the reason that I say that is because anything that might have been hard in position space is much, much harder in rotation space. Now, if you've never worked with 3D graphs and that sort of thing, you'll be like, I don't know what he's talking about, and that's true. Neither did I until I started working on these things. The problem with rotations is they don't obey the same kind of laws in 3 dimensions as we normally would like things to obey when we want to work with them. So for example, if you think about positions, and you think about the kind of laws they obey, they're really, really nice from a mathematical standpoint. Like, you don't have to sit down with someone and go like, okay, here's all the weird things that are going to happen with positions while you're working with them. No, they're just vectors. You add them, they're fine. You can move them around. Everything that you intuitively think will work will just work. But rotations are not that way. And the reason that they're not that way is because rotations, and I don't pretend to know even remotely enough abstract math to tell you why philosophically this is true. I can simply tell you practically, rotations don't obey commutation, like in the mathematical sense. If I do two rotations, A and B, I will not necessarily get the same rotation if I switch the order, right? With movement and positions, that sort of stuff doesn't happen. You can rearrange the order. It's nice computation. It's all the math things you want. But rotation is absolutely not that way. So at the time in 1999, my first sort of incarnation of the character animation system was using rotation matrices. You don't need to know what any of that stuff is. I just wanted a slide. Sometimes you just want a slide. You just want a slide in there when you're talking. You want something on the back. That's what it is. Got some like numbers. They've got some subscripts on them. It's great. So I was using rotation matrices, and rotation matrices are particularly inefficient for representing rotation because they're massively, 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 massively over degree of freedomed, if you will. A 3x3 matrix can do all sorts of things to your data. It can skew it, it can scale it, it can rotate it, it can do all kinds of stuff except move it. It's not affine, but it can do all sorts of stuff to your data, so it's really not a good representation for orientation because you've got way more information there that you need. Now, you may not think that's a big deal, but of course in the game industry, we care a lot about efficiency and these sorts of things. So typically, when you are using more data than you need, it ends up costing you in terms of efficiency, and not just in terms of storage. It also costs you in terms of speed, because if all of those values have to be correct in order for my program to work, that means I had to do work to get them there. So if the thing that I'm trying to represent only really needed 3 or 4 numbers, but I'm using 9, then that basically means I am 3 times worse than I should be. End of story, right? Okay. So the next paper that I want to talk about, this paper that I have loved, is Quaternions by Ken Shoemake. And this is a really interesting paper to me, and I picked it very specifically because it is the kind of paper that doesn't tell you anything new at all, literally. As far as I know, this paper has absolutely nothing in it that wasn't known by mathematicians many, many years before anyone even had a personal computer, let alone something that was new in the field at the time, right? So it's all old news. But it was the first paper that really made quaternions, which I'll tell you about in a second, as a rotation representation accessible to people who didn't want to spend a ton of time sifting through the math literature. And believe me, this is a real practical concern. It really doesn't have anything to do with whether or not you're good at math or whether you could be good at math. The bottom line is it takes a long time to work through dense math stuff, right? Even for people who are pretty good at it, you have to pay a lot of attention. It's very different if you just have a paper that goes, look, here's the high concepts, here's what you need to know, here's some code examples. That clicks really quickly. And for people who are programming on a budget, on a timeline, right, that makes a big difference. So I wanted to pick this one because of sort of that interesting aspect of it, and I'll tell you why I think that's important kind of at the end of this segment. How are we doing on time, by the way? Good? Thumbs up? All right. So quaternions are very odd things. I'm not going to try to explain them in this talk because I would need at least an hour to probably do that, really. But what a quaternion basically is a sort of extension of complex numbers, right? Complex numbers, we all know what they were. We had them in grade school. It's like when you have a real part and an imaginary part of a number, right? And you see it, it's usually written like a plus bi or something like this, right, depending on math things. I'm not a super math person, so who knows? But it's something like that. We've all seen it, right? Well, a quaternion is kind of, you can think of it a lot like that. It's a very similar concept in that you have these sort of additional bases that start stacking up after your comfortable real number, right? It's sort of like a comfort thing. It's a comfort thing, right? It's like, I'm really comfortable with the A, and the BI, it's like, oh man, I didn't study as hard that part of the math, so I'm a little nervous. Well, quaternions are like adding 2 more of those bad moments that you didn't study at the end, but there's a reason for it, so we'll get to it in a second. Anyway, so quaternions are kind of like a more complex number, a doubly complex number, or maybe a 3 times complex number if you want. When you write them, you typically just write the actual coefficients, obviously. The same way with a, if you're talking about a complex number, you typically don't bother writing the I all the time. You end up vectorizing and just saying, well, the top number is the real part and the bottom number is the imaginary part, whatever. So typically, quaternions are seen as just 4 numbers. And we all know we have some convention, let's say. I usually do them X, Y, Z, W. Some people do them W, X, Y, Z. But you kind of just know at some point that's what they are. So at some level, they're 4-dimensional vectors. But at some levels, they're not because they've got the structure behind them that we'll talk about in a second. All right. So what do they do? What they do at a high level is they encode orientation. And they encode orientation by their direction. Now, this is not how it is normally introduced, not even in that paper, but I can just say that that's sort of how it works. What happens is the length of a quaternion in 4 dimensions is not super relevant to the information that it encodes. It's only the direction. So if you imagined taking any quaternion that you had and like normalizing it so it was length 1, but still pointing in the same direction, you'd have the same information as far as what we care about in computer graphics, right? Now, that's not making a statement about quaternions in general, because there's probably plenty of times when you do care about that, but as far as encoding rotations in the way that we do, that's all that matters. So if you take a look on the right, there's a thing that says 2D, right? I'm just kind of drawing you a slice, because in 4D, I can't draw that. I don't know how to draw 4D. I have no idea. I can't even really think in 4D. I usually have to use analogies when I'm working with quaternions in my head to kind of like figure out what I need to do. But so in 2D, if you were to look at that diagram, the A and the B are the same rotation, right? Because one of them is just a longer vector than the other one, but they're both pointing in the same direction. So they would refer to the same orientation. The C, on the other hand, is a different orientation because it's pointing in a different direction, even though it's roughly the same length as A, right? So length is irrelevant, but direction is crucial. So just imagine that in 4D. I don't know if any of you went to, let's say Caltech. There's probably people who can't see in 4D. I'm not one of them. If you can, that's awesome. Now, the reason that these things were created and the reason that they have that weird structure with the IJK and all that stuff is because a guy named William Hamilton was trying to figure out literally this. This isn't one of those cases of borrowed mathematics where like computer games or graphics went and took some math that was for something else and used it for games or anything like this. This is actually what they were trying to do. They were trying to study mechanics problems, and they wanted ways of capturing what rotations do. So this guy named William Hamilton figured it out. This is not Alexander Hamilton, the guy that the musical's written about, although I think that would be awesome if they had like a musical about quaternions. I don't know what it would sound like, but I would like to hear it. So yeah, like I mentioned before, rotations don't commute. They're weird. And what Hamilton was trying to capture when he came up with this structure is that lack of commutation. So he wanted to have it so that if you do A and then B, you get C, and if you do B then A, same 2 rotations, you get a different rotation out, right? That's how it works in the real world, and they wanted the math to work that way, right? And he did it, right? That's why he's famous, well, math famous. He doesn't have a musical yet, but maybe someday he will when math is more important to society. Okay, so 3D rotations, if you were to say the words A then B, like I've been saying, apply rotation A, then apply rotation B. In matrices, it's just matrix multiplication. It's A times B, because matrices as well, and I suppose, again, not enough of an abstract math philosopher to tell you if there's like deep symmetry in the universe and this is why this works. Matrix multiplication also obeys this property. Matrix multiplication is not commutative. So if you encode rotations as matrices, like that wall of pretty x's and y's that I had up there before, you will get this property. So you can do it in matrices. Like I said, though, not very efficient. Quaternions have the exact same thing. So the multiplication operator in matrices and the multiplication operator in quaternions both obey that non-commutative property, which is why we like them. All right. But there's a reason we didn't like them in 1999. The reason we didn't like them in 1999 is because of that. I know that's an ironic thing to say, but one of the things that's true about when you're trying to do efficient computation is you always want to have it both ways. The best possible thing you can have in a representation is everything you want, not just one of the things that you want. And one of the things that you often do want when you're dealing with these things is non-order dependence, right? So I love the fact that when I'm trying to capture the order dependence of rotations, that I can do it. But I don't love the fact that in those parts of the code where I really don't want to care about the order, I have to care, right? And I'll motivate that a little bit more in a second here. So if I wanted to make an operator for quaternions where I did A op B and B op A, and I wanted to get the same result, we didn't know how to do it, right? We just didn't know. And the math didn't know either. Nobody knew. It was just not known. Okay. So why do we care, right? I'll tell you the solution in a second, but why do we care? The reason that we care is because typically what we're working with in animation, especially in the game industry, but equally as much pretty much in the film industry as well, and a lot of other cases, is a lot of times we have human input. On 2 ends of the scale. So I should say we have lots of human input on both ends. We have artists who need to make assets like animations and models and these sorts of things, and they make all that stuff at the game studio. And then we have players, and they've got a gamepad in their hand or a mouse and a keyboard or whatever, and they're doing lots of inputs to control those characters or whatever that's going on the screen, right? Pretty obvious game stuff. And the problem is those two things, right, need to sort of sync up, but we have no idea what's happening on one end of it. We don't know what the player is going to do. The whole point of games is the players get to do whatever they want. They can run around, they can jump off things, who knows what they're going to do, right? So we fundamentally, in the game industry, and then again, like I said, film industry, it's efficient to have these things, but in the game industry, it's a must. We need ways of authoring content where we don't actually know what the content is. We know something about what it might be, but we don't know exactly what it is. So typically what has to happen is we produce a bunch of possible asset cases, and then we need to be able to get to a specific like nobody ever authored it, a specific asset case at the end. And to give that a little more concrete flooring there, imagine that I had enough money to make art for the guy with his hand kind of waving at the top there, A, and then another one where the sad guy is kind of sad waving down in B. And I don't know what the player wants to set for how happy their character is. I want a whole range of happinesses, but I only had money for 2 happiest animations. So what I want to do is put in a % happy, right? I want % happy, and after I have % happy, then I'm going to get, on the other side, there's some kind of half happy, like we're not sure what's going on, a creepy neighbor wave or something. I don't know. But that's what we want, right? So in that context, we start to get into cases where we don't want to care about the order in which we're doing things, because this starts to multiply out. Let's say that I have more sort of axes on which I would like to do. I want % happy. I also want % something else. % hand size, like how big is the guy's hand. % coordination, is he like, does he not know what he's doing? So I might have sort of a whole multi-dimensional grid of samples, and I'm trying to get what it should look like in some specific area inside that thing, right? So at that point, I can't start really talking about order. There's just samples, and I'm weighting them or trying to grab them. All of the algorithms I might think about there, they don't have order involved. I'm not doing this, then that. I'm combining a set of things, and combining things, it doesn't really work that way, right? I want something more like the implicit surface thing we were talking about before, right? So I got all these fields, I add them together, and I get a thing out, right? That's what I want. Okay. So let me tell you now kind of what the solution to that problem was. So we had something at the time. It's called spherical linear interpolation. This is a thing that we actually had, right? It doesn't solve the problem at all, but it's something we actually had. And what spherical linear interpolation is, it's a lot like just regular linear interpolation, which probably, like a game development audience, everyone knows what linear interpolation is because you have to do it like 50 times a day, right? But probably a lot of people here don't know what linear interpolation is. Linear interpolation is really, really simple. It's just saying I have one thing, like the examples in that case in A and B, right? And I just want to linearly go between them using some percentage. Right? So I just want to get the things in the middle using some percentage. That's it, right? Well, spherical linear interpolation is the analog to that. It's the thing that does basically that. When instead of talking about linear motion through space or something else that's kind of along a line, I'm actually talking about an arc. Right? That's where the spherical in spherical linear interpolation is. It's just talking about going on an arc. And if you think about what I just said about quaternions before, which you probably can't because I'm going so fast it like fell off the thing, the like cache or whatever there. But if you think about what I said before, you can know why that would matter. It's because quaternions encode things by their direction, not their length. So when we talk about interpolating between them, what we're trying to do is interpolate their directions. And directions, when interpolated, move along an arc. So in order to move smoothly between two things and not have speed discontinuities there, we need to take into account the fact that we move along an arc and not a line, right? I know that's a little complicated to think about. It's 4 dimensions. What do you want, right? It's crazy, I know. Anyway, okay. So the question is, we had this slurp thing, and that was okay, it got us by a little bit. We could pick an arbitrary order and like slurp this thing to that thing, then slurp this other thing to this thing, and slurp this, right? But it starts to get really inefficient if you do that, and then what if you accidentally switch the order somewhere? The code now has to remember all the orders you might have done for certain things, because if you switch them wrong, you get a different result, and all of a sudden your thing would change frame to frame. Like there's all kinds of problems with it, right? And so the question was, could we design something that instead of having to do A to B, A to B, A to B, A to B, could we do something where we just fed everything in there and have that work, right? So fast forward to 2001. Spoiler warning for the 1999, 2000, 2001 years, I didn't solve the problem. So problem is not known. Still 2001, we have no idea what we're going to do about this. And to the extent to which, I thought I had a slide here for this. The extent to which we did not understand how to do this cannot be overstated. I'm not talking about us sitting around going like, oh, well, yeah, gosh, that's a hard problem. Maybe I'll think about that tomorrow. All right, let's go to lunch. I'm talking about people wrote dozens of papers on how to solve it that sucked, right? These papers were awful. They had to write like numerical like optimization things and just crazy things that we would never do at runtime in a game. Like forget about it, right? So it was really, really mysterious. So anyway, here's how we solved the problem. So the way that we ended up solving the problem was, we don't really understand this that well. Like we're using this slurp thing and we're using this math, and thanks to the papers that were kind of introductory about it, we sort of know how to use quaternions, but did we ever really look at how they actually work in practice, right? And so what we did is we wrote a program that could visualize how the slurp, right, that circular interpolation, was actually working in practice. And the way that it worked was you could put in two rotations, and it would draw coordinate frames for them. So again, if you're not familiar with computer graphics, this is going to be a little hard to relate to. But if you imagine two sets of like three-dimensional axes, right, like you might draw in math class, X, Y, Z axes, you could set two of those, right, and then you could look at what the interpolation was going to do between them. Okay? And it would draw the arcs between same axes. So when the x-axis would rotate to the other x-axis, it would show the arc between those. And then on the arc, it would mark notches to show where the interpolator was if it was at 0%, 10%, 20%, 30%, 40%, right? So it was a single static image that could show you this way that the interpolation happened, right? Now this was the first step. It took 4 hours. This was the first step that was going to be taken to try and solve this problem, right? It was like, let's just see what's going on. And it mapped, I'm just going to say, in that program, we mapped 4 things. Matrices, which I already told you about. The exponential map, which I'm skipping because it's more complex, so you don't need to know, but it was another way of doing interpolation. Slurp, and just for the heck of it, lerp, which is actually linear interpolation like the kind I said you do with regular things. So something that treats these quaternions just as if they were regular positions. So we don't even care. We throw out the fact that they're quaternions entirely, and we just run them through the same old code we would run through anything else, right? And to our surprise, what we found when we looked at the actual results of this is that lerp and slurp are almost identical for all of the angle distances that we ever cared about, right? So I've drawn 2 sets of notches here. The top one is lerp, the bottom one is slurp. You can see the bottom one is slightly more consistent. It's slightly more even speed, right? They're always going to be correct 0, 50, and 100% they're going to line up. Again, reasons we don't care about. But in between there, lerp on the sides is going to be a little bit, it's going to have just a little bit of a speed variance as it gets towards 0 and 100%. But they're really, really close together. And this was completely unexpected. Because we had always been thinking, oh, lerp, you can't use that. I mean, that's never going to work. Forget about lerp. No one even ever tried it. No one really ever even thought about it. But it turns out it's actually almost the same for everything we cared about, right? So that 4 hours, which was supposed to be the start of things, was actually the end of it. That was the answer. Once we knew that lerp could do this, and we didn't need slurp anymore, then it was trivial for us to do all the rest of our algorithms using this information, right? We could do n-way blending now because we could use the same sort of stuff we were using before, because now we can treat quaternions as positional values and get results we actually want. We can do faster 2-way blending because we no longer have to do inverse transcendentals. There is stuff in slurp that you don't want to do implementation-wise that makes it slow. You can do splines. You can do least squared fitting of splines, all of which we actually did in the character animation system. These were all things that we could do, and it was like awesome. It was a panacea. It was so good. And if you work backwards from that, right, which is always easier, hindsight's always 20/20, it's actually really obvious why this is true. But of course, if you never think that it might be true, you never think of the obvious answer as to why it is. But the reason that it's true is because if you think about what happens just in any space, forget 4 dimensions, just think about 2 dimensions. If I have 2 endpoints of 2 vectors, and I interpolate an arc between them, or I interpolate a line between them, well, if all I care about is the resulting direction, then it's just the projection of that line onto the arc. And we all know what happens when you project a line onto an arc, right? You get a little bit of bowing at the edges. It's correct in the middle and the 2 sides, right? It's exactly what we should have expected. But we never thought about it, so it wasn't ever really done, right? And by the way, as an aside, for those of you who might be math people or who care about this a little bit more, I'll point out that there's a reason why quaternions, lerp, and matrices don't really lerp very well. And it has to do with how they're encoded. There's an extra divide by 2. It's kind of an interesting thing. So if you care about that, talk to me after, and I can kind of give you a little bit more information. It's really neat, but it would take another 30 minutes to get there. OK. So in this case, dumb was like really good. Like being dumb was awesome, right? It turned out the simplest solution was definitely the best solution. And sometimes those are the ones that are hard to think of because you never think of looking in this place that's really dumb unless you happen upon it, like we did. And so one of the reasons I want to kind of plug this sort of paper is because if you think about what it took to get to this answer, it did not really take any math. There wasn't really any insight or mathematical or algebraic insight that led to this. What it took was just someone sitting down and bothering to write a bunch of code. And typically, often, many, many times, the people who will sit down and write things like visualizers aren't mathematicians, right? Trade programmers do programming all day. And they are very, very fast at writing fairly complicated software oftentimes. And they can do something like that really, really easily. But they may not have the algebra knowledge or whatever the math knowledge is necessary to understand quaternions from whole cloth or even know that they exist, right? They may not even know this, like so much mathematics out there, how do you even know it exists, right? And so one of the reasons that papers like this are so valuable is because you can get meaningful advancements in areas when you simply give people whose expertise is just making stuff access to the domain. And so this is one example of how that paper did that, but I bet there's lots of other examples too, because I know lots of people in our industry and probably other industries never would have learned about quaternions if it wasn't for that paper, and possibly since then there's been other ones, but who knows whether any of that would have happened for a long time if he hadn't written that paper. All right, how are we doing on time? I'm the last one. Still thumbs up? So now we'll go forward to 2003. And this is the last paper I have loved. All right, now I've talked about two types of papers I've loved, basically. One is, we came up with this cool algorithm, it solves a cool problem, and here it is, right? That was marching cubes. The other one is, I didn't come up with anything, but here's this cool thing in math, and I came up with a good way to explain it. And in some sense, in my mind, coming up with the explanation is almost an invention in itself. Because a lot of times, if you look at something, right, there's sometimes people who do all kinds of math and work with it, and they don't really understand it, not at the deep enough level to really communicate it in that intuitive way. So in some sense, Ken Shoemaker was doing real work there. It was a novel contribution, not just the writing. It's the coming up with how you explain something is real work. And that's a great paper, too. And now I'm going to talk about a third type of paper, and that is a paper that has a great contribution in terms of new ideas, new insights, just amazing, like mind-blowingly awesome, but is written by people who have absolutely no idea how to communicate that to anyone ever, right? Like it's basically like the most cryptic, it might as well be encrypted, right? Like with some kind of really strong encryption because no one's ever getting at the information in this paper. Okay. All right, so this is the paper. It's called A Fast Procedure for Computing Distance Between Complex Objects in Three-Dimensional Space, right? It's by 3 guys. They're from robotics, and it was a robotics paper. And I'm not going to try to explain it the way they explain it because it's nuts, right? I'm just going to explain it the way it actually works. Okay. The paper is full banana cakes. I'm borrowing that phrase from Jeff Roberts, guy who runs Rad Game Tools. It's a great phrase. The paper is full banana cakes. You read through it. It's got tons of notation to it, tons of lemmas, tons of all these sorts of things. It's like if you look back at section 231 where we proved this sort of thing, then you can see it follows directly that this. And you're like, I don't even remember that being mentioned. I don't even know what section you're talking about, right? Like that's the kind of paper it is, all right? So I'm going to explain it in a much, much more simpler way, but trust me, this is what the paper actually does in terms of what you care about. Okay. So let's say that I have 2 shapes. I've got shape A and I've got shape B. They're conveniently here, square and triangle. Of course, the 2 best shapes for illustrating collision detection. Everyone knows that. It's just a given. I won't try to justify it. All right. Let's say that these 2 shapes are intersecting. So I move A and B, and I move them in such a way that they are colliding in some way. They are taking up the same space, right? This paper is about figuring out whether that happened, right? This I want to get the answer, no, they are not colliding. Here, I want to get the answer, yes, they are colliding. And maybe I want other things too, like how much are they colliding or how far are they apart if they're not colliding, right? That's what I'm trying to do in this paper. So this paper, I'm not kidding when I say it's brilliant. It's one of those papers I look at and I'm like, wow, like this is crazy how smart you had to be to make these leaps, right? So the first thing that's pretty cool is it starts from a really interesting basic algebraic principle, which is rarely what you start with when you're dealing with something as concrete as collision detection of like shapes defined by their boundaries and stuff like that, which is a very discrete kind of a thing, right? But what they say is, well, hey, if 2 things are colliding, then we know that their interiors must have some points in common, right? Because I can't have 2 things that collide that don't share any points. It doesn't make any sense, right? They have to share some of their interior, otherwise we wouldn't consider them colliding, okay? And it turns out that we can write this in a mathematical way. We can actually say what that is. And what that is if I have A and I have B and they intersect, then I know that I should be able to find at least one point on A and at least one point on B that are the same point, right? They have to be the same point in the world. Because otherwise, if I couldn't find any points that had that be true, then obviously these things don't intersect. They don't occupy the same space, right? And with trivial subtraction, I can say equivalently that somewhere there are 2 points which when I subtract one from the other, I will get 0. There is no separation between these points. And again, I'm just talking about one pair. I have to be able to find just one pair. And if I can find even one pair, then they intersect. Maybe only at one point, but they intersect somewhere. Okay. Now, second crazy leap in this one, because that's kind of smart to begin with. I don't know, maybe it doesn't sound smart to you, but it was literally something I never even thought about until this paper. It was like, oh yeah, right, duh, you can do that, but I never thought about it. So they were thinking of it from like these interesting first principles of collision, like molecules in the world occupying the same space or something. It was kind of cool. Okay, next one is, well, okay, what good does that do me? Right? It doesn't really seem to do me any good. Because what am I going to do? Iterate through all the points in the object and subtract the 2 and see? It's like, it's not only is it an n squared problem, but the n is infinite. Because there's an infinite number of points in a shape, right? So this doesn't seem very good. Even if we're talking about discrete representations in a computer, there's way too many of them. But they borrowed something called the Minkowski sum, which is an algebraic thing that allows you to add shapes together. And I'm not kidding, this actually is a thing, a real piece of mathematics. It's not someone's weird like art demo or something. Real mathematics where you can add shapes together for real mathematically. Okay? And what this is if you imagine I take a rectangle and I add a circle, I get a rounded rectangle, right? It's like I'm adding these 2 shapes together, and they are both represented in it. Now, how do you form this? Well, the way that you form it is you imagine taking one of the shapes, and you put the other shape in that shape everywhere it can go, right? So I take if I took my circle, let me go back to the slide just so you can be clear on it. If I take my circle and my square, you can see the origins of them. If I take the origin of my circle there, that center point, and I put it inside the square. You can look on the left side of the diagram. Put it inside the square, and I move it all around everywhere it could possibly go. I constrain it by the edges, but I move it all around everywhere else. And I take the resulting shape everywhere I ever filled when I did that, and I get the result, right? So it's very rigorously mathematically defined. It is not hand-waving when you say, I take a rectangle and a circle, I add them together and get a rounded rectangle. No hand-waving. It actually works, and it works for any kind of shape that you might throw at it. So on the other side, I did like a weird, quadrilateral and a triangle, right? And you can do it with anything. You can do it with a teapot and a ring. You can do it with everything you want. You will get it. And you can do it in any dimensions you want. It's just a true thing about filling volumes, okay? Now, there's something very specific about this, because this is math, not art. Right? Although math is kind of an art sometimes. I don't know. I don't want to bias you in a way of thinking about it. But point being, it's rigorous, let's say. Let's use that word. Because art could be rigorous too if it wanted to be. So it's rigorous in that the origin position matters. So when I define these shapes, they are actually a set of points for reals with an origin and values. What that means is that if I perform the Minkowski sum, and one of my shapes is offset from its origin, so it's not a circle centered about the origin, that displacement actually occurs when I do that sweep. Remember I said you put the origin everywhere inside the first shape, right? Not the shape itself. The origin goes everywhere, and then I get the result. So if there is a net displacement of one of the shapes, that net displacement will occur in the result. Okay? That's really important. I'm not just saying that because I think it's cool. It's really important to the result. Okay. And what you can kind of see here is I wanted to sort of illustrate that a little further. But if you go back to what I said in the first sort of slide about this, when I put up that algebra, I said I should be able to find one point A and one point B, whereas if I subtract them, I get 0. Right? I said I want to take some point in A, some point in B. I want to subtract them and get 0. Well, if you think about what happens when I start transforming the problem into this Minkowski sum space, right? Well, what I'm really talking about is I want to be able to find whether there were any points, in this entire thing where if I subtracted the 2 of them, I would have gotten 0. And 0 in that equation, right? 0 is the origin in the Minkowski sum, right? Because if I took one shape and I subtracted it from the other shape, if they had any points in common, the origin would lie inside the resulting shape. Right? Because some 2 points at some point subtracted out to 0, right? And that's the interesting thing about the Minkowski sum is, again, not an arbitrary definition. It really is effectively subtracting all points from all other points. That is the result that it's giving you. It's just doing it in kind of a more theoretical fashion, right? A little hard to understand. I'm sorry if that's rough. That's the only rough part of this. Everything else, easy. Okay. So if you take a look at what happens here, I said A minus B. right? I said I want to take some point on A and some point on B and subtract them. But the only thing I talked about doing before is summing two shapes together, right? And summing is not actually what I wanted. I didn't want A plus B, I wanted A minus B. But it's trivial to turn A plus B into A minus B by just negating all the points, right? So on the top, I have an example of square minus circle. On the bottom, all I've done is negate the circle and turned it into a sum. So even though Minkowski doesn't technically define a Minkowski difference, it doesn't matter because it's just a sum with a negative, all right? Just want to get that out of the way for people who care. Okay. Now, by the way, when I did this, right, before, if you imagine taking that origin and putting them, let's say I had those two shapes now, and I'm talking about collision detection again. I want to know, does the circle and the square, do they collide or don't they, right? This was the case I had, and here was them, sort of broken out. I do the subtraction, I see where the origin is, the origin's outside the shape. And hey, that's the right result. These two shapes aren't intersecting, so the origin isn't inside the resulting shape. Okay. How bad is that? Anyone really feeling like, nah, I don't get it. I don't get it. It's okay. I'm sure I didn't get it the first time either, so you're actually a kindred spirit if you didn't. Seriously? Oh, all right. Okay. So here's the next insight, because there's insight upon insight in this paper. The next insight is, well, okay. For concave shapes, if I were to perform the Minkowski sum, right, I would get a concave shape if I add a concave shape to anything else, most of the time, right? I certainly can't guarantee anything about it. It'll probably be concave. And the reason it'll probably be concave is because when you do this sum, usually the features of both shapes come through. So if one of the shapes is concave and I add it to the other shape, well, I'm probably going to get a concave shape out the other side. Now, it may happen that the shapes themselves just happen to work in a way that it cancels out the concavity, but that's certainly not a guarantee, and you can't base an algorithm on it. However, if they are convex, then when I add them together, I will always get a convex shape. And why? Because there is no place for the concavity to come from, right? I'm only adding solids together, so all they can do is inflate each other. They can never create sort of an inscuse or like a crenellation, because I never had any to start with. And remember, all the definition of this thing is all the points plus all the other points, right? Okay, so reason I call that an insight and not an observation is because you had to figure out that you even cared about that. But you do care about that. And the reason that you care about that is the next insight in this paper. And that is that for convex shapes, right? For convex shapes, for every point on the convex shape, there is some direction that I can pick where it is the furthest. I can never, ever, ever pick a point where some other point is always going to be further along any direction I might pick, right? So take a look on the left. You can see all of the points have some direction I could pick where they're the furthest. There is no other point that supersedes them. But on the right, you can see that that is not true. There's a concave shape, and that point in the middle, no matter what direction I can pick any direction I want, there is always some other point that's further along that direction, right? Always some other point. I challenge you to do it. If you can do it, come up after and tell me. You've broken mathematics. But this turns out to be incredibly important. Why, right? This is why I call these insights, because even recounting them with the knowledge that it's true, I have to spend a lot of time explaining to you why these things are important. That's how crazy insightful these people were. The reason is because let's suppose, 5 minutes? Is that what that is? Okay, we're almost done. That's actually not that bad. I'll speed back up. Okay, so let's suppose that we have one of these Minkowski sums, right? And one of the things that we're going to have to do in a second here is just realize the fact that, well, okay, that stuff I talked about with the Minkowski sum, it's abstract mathematics, right? But if you think about what actually has to happen if I wanted to start computing with them, if I was computing directly with Minkowski sums, I'm in a lot of trouble, right? Even just the thing I said that was an easy way to visualize subtracting all the shapes from the other shapes or anything like that is incredibly difficult to do. How would I even write the algorithm that sweeps this shape around the other shape? Okay, now I need to have something that actually does that and tessellate the geometry of it, and there could be robustness problems and blah, 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 right? It's like, starts to be a real scary thing, right? So what I'm aiming for at this point, is I need some way of doing computations with these Minkowski sums that doesn't involve actually ever building them. Because if I ever had to actually build a Minkowski sum, this algorithm is going to be awful, right? So I need some shortcut. And here it is. Using that knowledge that I talked about before on the fact that for any convex shape, there's always a point, for any point, there's always a direction where it's the furthest along. I can pick random directions, right? And I can find the points that are furthest along. And if I do that in several directions, I will eventually form a volume or a solid or an area in 2D, right? And that area is guaranteed to be part of the resulting shape. It's completely contained inside it. There is nothing in there that isn't also inside the Minkowski sum. That's really important because now we can work with it. If this was a concave shape, you can imagine if the bottom was just poking up, that wouldn't be true anymore. Not everything inside my triangle would have been inside the Minkowski sum. So I need this way of building partial things, and now I've got it. I can pick arbitrary directions, I can find points on the Minkowski sum, on their boundary, and I can do it. But you're saying, okay, well, Casey, all right, okay, maybe I sort of see what you're saying there a little bit, but okay, in order to find the points that are furthest away, right, I'd have to build the Minkowski sum again. You just said you didn't want to do that. You're contradicting yourself. It's like, okay, yes, maybe I am. That's why there's yet another insight, right? And that insight is that when I do the Minkowski sum, because it is a sum, if I just do that operation on the individual shapes I'm summing first, I can add the results. So what that means is I can just take the two shapes that I was inputting, find the furthest point on those, and add the results together. And that's trivial. We can all easily figure out for any shape, right? For any mesh we actually have that we want to input, or any shape we want to do, we can easily find the point that's that far in the direction. We just do that for our input shapes, we add them together, and we're done. We've never constructed the Minkowski sum of those shapes, but we found a point on its surface without ever even making it, right? And this is kind of amazing. It's super, super cool. Okay, so let's go ahead and just give credit to the person who actually figured out the part here that I'm about to say. So I was talking about how this had to be talk about papers that led us to do something cool. Well, the something cool here was figuring out how to actually implement this algorithm really efficiently. And I'm going to explain it the way that we implement it, which is really efficient because it only takes about 5 seconds to explain, and we're running out of time, so that's good. But the actual paper itself was so obtuse that they actually, I think, maybe missed what was actually going on in the algorithm. They kind of used a bunch of math to get to the result, but it was a very expensive set of steps that they used. And it turns out that if you think about the problem more intuitively, you can actually do it in a much more efficient way. So I want to give credit to Jay Stelly for that, because he's the guy who actually figured out that sort of intuitive way of looking at it, and it's what led to the way that you can actually implement it really efficiently. Okay, and I'll skip what he actually said because we're low on time. All right, so just to recap, here's what we have going to the algorithm. We have a function, and I didn't say it was on the title of the slide before, but it's called the support function, the thing that tells you that point. I give you a direction, you tell me the point on the Minkowski sum that's the furthest one in that direction, right? We have that, we want to do our actual intersection test. Okay, so here's how it goes. First, we pick any support direction. We say, what's the point? We get a point. It's the point down the lower left corner. We know where the origin is because the origin is at 0, 0, 0. So we just know where it is, right? Then we say, okay, in the direction of the origin, that's the next support function call. So give me the point that's as far in that direction as it possibly can be. And already, just with those two steps, which hopefully are very easy to understand, we can know whether we've intersected or not, whether these two shapes are intersecting or not. We have our first clue. If the point is not on the other side of the origin when viewed from the perspective of that direction we're going, then the shapes can't intersect. Because if that's the furthest point, that one I've gotten there, if that's the furthest point in that direction, how would I ever enclose the origin? The resulting shape could never enclose the origin. There's nothing beyond that line. There's no way to ever enclose the origin. It's on the other side of it, right? So I already have an early termination condition. If I couldn't get past the origin, the Minkowski sum that I'm looking at must never have enclosed it, because if it did, I should have gotten a point that was on the other side, right? But let's say that I got back the opposite result. I did get a point on the Minkowski sum boundary that's on the other side of it, right? Now all I do is I continue. I say, take that edge that I've gotten, go in a perpendicular direction to it, and give me the next support point, right? Now I've got a triangle. Once I have a triangle, I can test to see whether the origin is inside the triangle. If the origin is inside the triangle, remember this is a triangle that is in the Minkowski sum. It's inside that shape, right? If that contains it, we're done. The shapes intersect, because 0 is in there. So 2 points, you must be able to find 2 points in the object that can subtract to it, right? If I don't, if for some reason the origin was outside it, then again I can just actually loop, because all I do is pick whichever edge it was closest to, and you can see I've drawn the regions there, A or B. If, let's say, the origin wasn't inside the triangle, instead the origin was in the A space, or the origin was in the B space, all I do is I just pick the edge that was closest to that space. So if it's the B space, it's that B edge there. If it's the A space, it's the A edge. And go back, go back to this step, right? Go back to the edge step with that new edge. All you do is iterate that till you get one of those two conditions. Either the failure case where you can't enclose the origin, or the case where the triangle that you've got encloses the origin. That's the entire algorithm. That's it. It's trivial to implement. Implementing it takes no time at all, right? All you have to do is implement that little bit of movement math that I just said there, and the support function thing, taking your two shapes and adding them. And right there, you've got something that can do almost anything. It's crazy what this thing can do, because the Minkowski sums are actually generalized, right? That support function distributes over any number of operators, which means that the two things that I collide when I pass to it, I could actually do summed objects that are collided. So I could do my rounded rectangle case and a swept triangle case, and I could actually do the Minkowski sum of those first, then do the subtract, and so I can collide shapes that I can't even really find the result of, right? Which is even awesomer. Furthermore, it works in 3D. All you need to do is in that triangle case, you extend it to a tetrahedral case. It's really no more work. So it's even something that works, I won't say in arbitrary dimensions, though I think you probably could. It works in 3 dimensions just as easily, right? OK, so now we're at the end of the talk, which hopefully I'm not too far over time. I told them I was going to be over time, so I feel like that's OK. But end of the talk is that true? How bad am I? OK. I said at the beginning of the talk that, OK, these are things that led to something cool. If you remember the marching cubes thing, I never told you it leading to something cool. I just said, hey, there's marching cubes, we did it. Well, what did we, OK, great, whatever. Well, it turns out that this is kind of like one of those you know, like in the movies where like the bad guy is like dead and he's burned and he's lying in like a ditch or whatever. And then like, you know, at the very last frame of the movie, like his hand comes up or whatever, and he's like, he's not dead. He's going to come back in like a sequel or something. That is kind of like how this talk ends. So basically that marching cubes thing, recently, like he was saying, one of the most recent games I worked on was The Witness. And it turns out this is 20 years after, right? This is 20 years after I first read the marching cubes paper. And we were trying to do a walk system that had some really interesting constraints. We wanted like all these robustness guarantees and stuff like this. And it turned out that the way that I ended up solving the problem is based largely on that initial marching cube stuff that I remembered from 20 years prior. So really, there's never a time when reading a paper is not potentially going to stay with you and be useful. So that was about it. And yeah, there's my contact info. And sorry it went so fast, but like I said, there's a lot of stuff in there I wanted to not miss any of it. So thank you very much.
We'll take a couple questions. Go for it.
Do we have time for questions?
Hello.
Oh, OK.
Hi.
Yes.
Just a question regarding lerp and slurp.
Sorry? Oh, slurp and slurp, yeah.
Slurp and lerp. It seems that you can get, like with lerp, you can get the exact midpoint. And if you can get the exact midpoint in logarithmic time, you can get the exact slurp.
Yes, you can. It's basically like bicep. But remember, what we're trying to do is do it as fast as possible. And so if you have to keep doing those computations, it's way too costly, right? Okay. If that makes sense. Because slurp itself, if you want to implement slurp, all it is an atan. It's an inverse transcendental, and then you can get anywhere you want. So if you start bisecting, you're going to take a lot longer than that, if that makes sense. So yeah, you can do it that way, and then it's, you know, but it doesn't actually help in that particular case, if that makes sense.
When you were doing slurp, you talked about doing a rotational pass and therefore length of the WXYZ vector doesn't matter. But
yes.
When you're doing lerp, I assume length does matter because you're having to take the equal points for equal distance. So then were you having to normalize that vector for length before you do that?
Got it. So the answer to that question is definitely. And I cut out a ton of stuff, right, because it was just kind of give the basics. In actuality, there's a lot of things you care about, all of which are actually fairly easy to manage, but which you do need to know. Some of them are, yes, once you switch from slurp to lerp, and I think actually potentially even in slurp, I don't quite remember, you do have issues where you want to try and keep these values actually close together, because otherwise you'll see artifacts of that potentially in there. The other one is quaternions have this other property, which is actually a really important property for physics and all these other sorts of things, which is that actually it doesn't encode only the rotations that we think about in the real world, but actually an additional set of rotations. It's actually double covered is what it's called, where you can actually represent 360-degree rotations and then another 360 degrees that aren't the same. And I know this sounds really weird, but if you're into theoretical physics or whatever, go look up double cover or rotations or that sort of thing, and it'll explain more about it. But because of that, you also have this other thing called neighborhooding that you have to do. So there's actually, it's not like it just magically works in a way that you don't have to understand anything. You still have to understand it all, and when you do the pipeline, it's actually very easy to set it up so that it all works properly, but you do have to know all the things like the one that you're talking about and a couple other that I didn't mention. So I don't want people to get the wrong idea that that's like all you need to do. It's like there is a lot more to it, but in terms of the actual computation, yeah.
Maybe one more question? Anyone has one? All right. Thank you, Casey.
Okay.